two things with right triangles. We're going to look at similar right triangles, these kind in particular, and some special right triangles. So let's start with the similar right triangle. Let's do a little bit of review. Geometric mean. Do you guys remember geometric mean? Some of us never learned that. I learned that on the last test as well. So for once and for all, geometric mean. If I have two numbers, A and B, how do I find the geometric mean? How do I find it? Multiply them and do what? Take the square root. The square root of the product. So the square root of A times B. That's how you find a geometric mean. Right? Right? Right. Okay. What else do we need to review? Oh yeah, find the geometric mean of 9 and 16. How do I do that? How do I do that? It's like, you know what an arithmetic mean is? Where you add numbers and you divide by the number of numbers. This is analogous to that. It is, now you're multiplying and taking the nth root. So geometric mean is, well, if you're taking geometric means, I'm trying to think of 3 times 5 is 15, plus 5, 16 times 5, 75. So the geometric mean is what you divide by to get a previous number. So this geometric mean here is 5. Because to make a geometric series, I would multiply all the numbers by 5 or divide by 5 to go backwards. So that's what it is. And it's analogous to an arithmetic mean, except you find it by finding the nth root of a product of n numbers. So I don't know if that helps at all. But we're only worrying about 2. So if you have 2 numbers and you want their geometric mean, so 3 times 75, take the square root. I hope we get the 16. Well, actually, I'm sorry. This is the geometric mean. This is probably, this has a name, and it's lost. I've lost it. There's some kind of factor, and I can't remember the name. But that's the mean. It's the number in between 2 numbers in a geometric series. Maybe that's the way of saying it. Okay. Okay. So how do I find this then? Yeah, Kate?
Multiply 9 times 16, and then put the square root in.
Okay, what's that calculator?
How do you?
It's 9 times 16.
144.
Okay, so what is this? So the geometric mean, if you had a geometric series, the 12 is in 2. All right, what's altitude? We did a little bit with altitude. You remember what it is? Height. It is. It's the height of a triangle. Or any figure. It's its height. So it's drawn from the vertex to the opposite side of the vertex, and it's what? To the side it touches? Yeah? Perpendicular. So altitudes are perpendicular lengths, and that's how I know how the height of this triangle. Is it necessarily a bisector? Not necessarily. It could be, but not necessarily. It's just from a vertex, you just drop a line. There it is. And it's like you drop a penny from an airplane. I think of that. It's always going to be perpendicular to that flat surface that it's on. So those are things we need to know. Similar right triangles. So if the altitude is drawn to the hypotenuse of a right triangle, and the 2 triangles are formed, and what 2 triangles are formed? So I've got this triangle, and I've got this triangle. It's similar to the original triangle, and I hope this works. Let me check this out a bit. So let's see if this works. It kind of shows the different triangles that are formed. There it is. Let's see if this works. So here's a right triangle, and I don't want this. Everything's an ad nowadays, isn't it? Let's see what it is. Wow. There we go. There's a little beautiful thing here. Yeah, I see that, but it doesn't look like it looks here, you can look at it. So here we go. I have a right triangle. I drop an altitude, and I've actually got 3 triangles now. This little guy, this bigger guy, and the original one. So let's see if we can split them apart. There we go. There's one of them. Let's see the next one. There's that guy. And then the big one. And watch, we kind of turn. And we flip it around. And these are the three similar triangles that are formed when we do this. Similar, okay? So that's going to be helpful for us. Let's see if we can work this out here. So if I kind of break them apart, so remember we had to kind of flip this one a tiny bit. We rotated it actually. This one kind of came out as is. And the big triangle, I kind of had to turn, rotate, and flip around to see it. So let's see, what are my similar triangles here? So ABC is similar to CBD. That's 3 to 1 are similar. ABC is similar to ACD. 3 is similar to 2. And CBD is similar to ACD, yes? They're all similar triangles. So let's see, I'm looking at them up here now. So triangle 1, which is my little one here, and triangles 2 are similar. Compare the shorter leg to the longer leg. So BD is to CD as CD is to AD. Now this CD and CD have the same name, right? How come? Because remember, it's this way. They're still part of one kind of shape. So even though they look like separate triangles, they're not. These are attached. So does this proportion make sense? You know, once I pulled apart the triangles. Do you see it, or is this still a little hard to see? Stay with me. Anybody with me? Nobody. Thank you, 3 people. All right, let's look at triangle 3 and 1. The small one with the bigger one. So what do I have here? Compare the hypotenuse to the shorter leg. So AB to CB, right? Those are the matching sides. Equals CB to BB, right? They match. Just looking for corresponding sides so I can set up my proportion. And then 3 and 2, what do I have here? I have AB to AC, so looking at the hypotenuse, compared to this side here, AC to AD. How do we feel about these proportions? Do they make sense to us? You see them? Okay, good. So now what can we do with them? It says CD, the altitude of triangle ABC, this guy right here. It's the geometric mean of BD and AD. Where am I getting that from? Well, look at this guy. Remember how we can solve this kind of? Remember cross products? Who says, if you remember cross products, say yes.
Yes.
Okay. So what does that mean? CD times CD. And CD times CD is CD squared equals BD times AD. Doesn't it? Cross products? So take the square root of both sides. What's CD? It's the square root of BD, times AD. Isn't that geometric mean? Multiply 2 things, take the square root. So this statement says that CD, this guy right here, is the geometric mean of BD, this piece, and this piece. This geometric mean, this piece, and this piece. What else? CB, a leg of triangle ABC. Here's CB, that's this guy. It's the geometric mean of AB, this whole side, and DB, this little short side. That's part of like CB's little triangle there. Let's see how that happens. Well, look what's happening here. In this proportion, CB times CB, which is CB squared, is the same as the product of AB times BB, right? AB times BB, which means what? CB is the square root of AB times BB. Geometric mean. These 2 things, geometric mean. So let's look at it again. This side right here is the geometric mean of this little piece kind of right adjacent to it and that whole side. What else do we know? The other leg, AC, is the geometric mean of AB. Again, that whole thing and AB, the piece of it closest to AC. And where's that coming from? Cross product. AC times AC, AC squared equals that times that, AB times AB. And what does that mean? That AC is the square root of AB times AB. And that's geometric mean. Take the product of 2 numbers and its square root, you have geometric mean. So let's see what we got here. This piece coming down, that altitude is the geometric mean of the 2 pieces it creates. A leg is the geometric mean of the small piece adjacent to it and the entire piece. This leg is the geometric mean of the small piece adjacent to it, AB, and the entire thing. Everybody following that? Thank you, 2 people, 3 people, awesome. All right, so let's see what we got here. In a right triangle, these are the theorems now. The altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. The geometric mean altitude theorem. The length of the altitude, remember what that is, that's that piece you drop that's perpendicular to the other side, is the geometric mean of the 2 segments, AD and BD. CD is the geometric mean of AD times BD. And then the geometric mean leg theorem, the length of each leg of this right triangle, here's a leg, there's a leg, is the geometric mean of the length of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Oh, that's a big long thing. What this means, CCD? CD is the geometric mean of this little piece adjacent to it, DD. And here's the tricky bit, not really tricky, you just have to remember it. And the whole hypotenuse, AD. So then what would AC be, the other leg? Anybody want to take a guess? What's AC going to be the geometric mean of? Yeah? Exactly. The piece adjacent, the segment that's adjacent to the piece you're trying to find, the leg you're trying to find, and the entire hypotenuse. Yes. Yes, always can look like this. Because remember, we ripped apart the similarities of the triangles, and we could see those proportions if this was going to happen. Now, can you always just rip apart the triangles and use the similar sides? You can, but I tell you, it's confusing. And once you kind of master this, it's much, much easier. Let's see if I have some examples here. Find the value of the variables. I'm just kind of repeating the theorem. So x, I have the situation. I have a right triangle, and I drop in altitude. So how do I find x? I want to hazard a guess here. What is x the geometric mean of? Yeah? 15 and 10. So x is the geometric mean of 15 and 10. Which means I have to multiply that guy. So it is the square root of 150. It says the simplest radical form. So now I got to look and see if there are perfect square factors in here. Ooh, there's a good one in here, right? 25 times what is 150? Yep. Now 25 is a perfect square. 5 radical 6. Now what if it said, to the nearest tenth, find this? Well, what would I do? That's a little bit easier. I just go to my calculator. Okay, let's break it in. It's going to be the square root of 15 times 10. To the nearest tenth, what is it? 12.2? If they wanted that. Okay, now this guy, right, do you know where we are? We're kind of at the bottom of the page here. This guy, I'm looking for a leg. Now I'm looking for a leg. So let's see, how do I find that? What is it the geometric mean of? Yeah, Maria? Yeah. 8, the little piece that's adjacent to it, and the entire length of that hypotenuse. 26. Oops. I don't know, what's 8 times 26? Do I have a calculator with you? 8 times 26? 208. So that's the square root of 208. That's why. But it says simplest radical form. Are there any perfect squares hiding in there? Yeah, there are. There are. You know what it is? There's a bigger one. 16 times 13? Yeah? So square root of 16 is 4 radical 13. Which is the simplest radical form? Is that it said to the nearest 10. If it's to the nearest 10, then let me just type it in. Take the square root of 18 times 10. What is it to the nearest 10? 14.4. Okay. Cool. Alright, well, wow, what am I going to do with this guy? To find y, is y the geometric mean of 6 and 8? Now think about what the theorem states. What is y the geometric mean of? So this little piece here I'm going to call it A, and this little piece here B. But I don't know what they are. Oh. What do I know? Now this is a right triangle, right? If this is 6 and this is 8, what's the hypotenuse? 10. How'd you get 10? It is a 3, 4, 5 triangle, but it's by times 2. The 3, 4, 5 triangle times 2. If you don't see it, use the Pythagorean theorem. It's going to be square root of 6 squared plus 8 squared. 10. Get a little closer. Can I find A? The answer to that question is yes. How can I find A? Well, if the 6 is the geometric mean of what? A times 10, right, isn't it? The leg is the geometric mean of the piece adjacent to it times the whole thing. So now how do I get A out of that thing? How do I get it out of here? What do I do? Well, how about just squaring everything? What's the square of 6 is 36, right? What's the square root of 8 times 10? Which I guess I'll turn it around as 10 times A. So then what's A? And I'm just going to leave it as one of these guys. It says to the nearest 10. Saving me here. 3.6. What should B be? This whole thing is 10, and this is 3.6. What? Can I find B? Yeah, how can I find B? How can I find B? 10 minus 3.6, which is? What? Now, is there a way to check that I'm right? Because sometimes, what if I mess this up? Isn't that messing this one up? What's another way I can find it? Yeah? How about this? Yeah. This is the geometric mean of what? B times 10. I'll turn it around now. So then how am I going to get B? Square both sides. 64 equals 10B. Divide both sides by 10. B equals 6.4. So I'm in pretty good shape. Great! Why am I doing this again? Oh yeah, I want to find Y. How can I find Y? Y is the geometric mean of these two things. So what can I do, Lydia? So 3.6 times 6.4. Luckily to the nearest 10, I'm just taking out the calculator here. So it's going to be the square root of 3.6 times 6.4. And to the nearest 10, oh, it is to the nearest 10. Y equals 4.1. Wow. So this can get a little complicated, but as long as we remember those basic theorems, this guy is the geometric mean of the two pieces it creates, and each leg is the geometric mean of the closest segment and the entire piece of the hypotenuse. Questions? Not yet. Okay. That's all there is to it. Okay. Next little topic, special right triangles. It's nice to be special. We're going to use the Pythagorean theorem here. You're going to help me out here. So this is a right triangle. This is 5 and this is 5. How do I find x? How do I do this? Yeah, what do I do? 25 plus 24, that's 50, right? So x equals the square root of 50. What is that in simplest radical form? Yeah? 5 rad 2. How do you get 5 rad 2? 25 times 2, square root of 25 is 5. So x is 5 rad 2. Okay. How about this guy? How do I find this square root? Or how do I find x here? Yeah? What do I have here? X squared plus 9 equals, ooh, okay, so what is 3 rad 2 squared? Yeah? 18. How come? Right, 3 times 3 is 9. Times square root 2 times the square root of 2 is 2. 9 times 2 is 18. So x squared, subtract 9 from both sides. What's x? We're going to take the positive root. Great. Okay. by 6 rad 2. So let me erase some of the jazz here we got going. And just look at the values that we got here. I've got 5, 5, 5 radical 2, 3, 3, 3 radical 2, 6 radical 2, 6 radical 2, 12. And I'm noticing these are all 45, 45, 45, 45. Can we see a pattern? Can you see a pattern? What is it? Wait, oh, try. What do you think's happening? Well, what's happening in these two? First of all, what do I know about the sides? Yeah. The same. How come? Well, we have that theorem, right? If you have two base angles that are congruent, don't I know the opposite sides are congruent? Because you're going to be isosceles. And what are we noticing about the hypotenuse here? Leg times the square root of 2. That's true for this one. Well, if you take the leg and you multiply by square root 2, what do you get? Well, what's rad 2 times rad 2? 2 times 6. Oh, it works for this one also. So the hypotenuse is the leg times the square root of 2. So what would the hypotenuse be in an isosceles right triangle with a leg of length 1? Just the square root of 2. We can kind of look at a general case. So what if the leg is 10? What's the hypotenuse? You have one of these. This is a 45, 45, 90 triangle. It's a special triangle. What if each leg is 10? Without having to use the Pythagorean theorem or anything, what is the hypotenuse? 10 rad 2. That's it. That's as easy as it gets, right? What if this was 100? 100 rad 2. Now let's go the other way. Oh, goodness gracious. What if we have a 45, 45, 90? What a horrible looking triangle. And the leg is 20, I'm sorry, the hypotenuse is 20 rad 2. What's the leg? 20. Now how do you get there? Divide by radical 2. So if they give you the hypotenuse, it's in the 45, 45, 90, you divide by 2, radical 2 to get the leg. And if they give you a leg or legs, doesn't matter, you only need one, right? Because if they only give you one leg, what's the other one? Same thing, because these are 45, 45, it's going to be an isosceles triangle. Multiply by square root 2. That's it. Right there. So in a 45, 45, 90 triangle, it's an isosceles right triangle. The hypotenuse is square root 2 times as long as the leg. Now if you want to find the leg given a hypotenuse, you divide by the square root of 2. So here's the Pythagorean theorem. It's going to generalize the situation. So a squared plus a squared is going to be our c squared, right? Well, what is a squared plus a squared? It's 2a squared. So I want the square root of this, right? That's c squared. So if I want c, I need the square root of 2a squared. Well, square root of 2, can I take the square root of 2? So that's going to stay inside. What's the square root of a squared? So there it is. So we can generalize. A squared plus times a squared plus a squared is a rad 2. Just generalizing it so we can remember it. Not so bad. So if you forget, make this little triangle. You can get back there. Okay, so this 30, 60, 90. This is the other special triangle. 30 degrees, 60 degrees, 90 right triangle. So again, let's use the Pythagorean theorem to find x. So what do we have here? 5 squared plus this thing squared is going to be our x squared. So 25 plus 25 times 3, right? 75 is 100, which is x squared. So what's x? Did we follow what happened here? Did we follow that? Yeah? Okay. Let's try this guy now. Let's see, we'll face here. X squared plus, what is 4 rad 3, that whole thing squared? 4 times 4. 16. Rad 3 times rad 3, 3. 16 times 3 equals 8 squared. Okay, so that means that x squared equals, what's 64 minus 48? So what's x? Alrighty, let's squares hiding in there? Yes. Nine? 9 times what? Well, 12 also has a perfect square in there, right? 4. So 9 times 4 is 36. So 36 must be what? 36 times what is 108? 3? So this is 6 rad 3. So again, let's see if I can erase some of the jazz here, some of this work. And we start seeing a pattern. You see any pattern for me? 5, 5 rad 3, 10. 4, 4 rad 3, 8. 6, 6 rad 3, 12. Yeah? Yes. Okay, so the side opposite the 30, the smaller side, half the hypotenuse. Looks for all of them. What else? What can I say about the side, the bigger side, opposite 60? So it's the smaller side times radical 3. Does that work? So the 30 degree, the side opposite the 30 is half the hypotenuse. The side opposite the 60 is the side opposite the 30 times the radical 3. So let's see. The hypotenuse is the shorter leg times 2. Yeah? Shorter leg times 2. The longer leg is the shorter leg times the square root of 3. So looking at kind of a simpler looking triangle, the shorter leg is 1. So that means double it to get the hypotenuse, which is 2. And multiply it by the square root of 3 to get the shorter side. So what would the hypotenuse be? It would be 2. And the longer length is 1 times the square root of 3. So let's see. The hypotenuse is 2 times the shorter leg. The longer leg is the shorter leg times square root of 3. Or, if you're given a hypotenuse and you want to find the shorter leg, divide by 2. Or you can take the longer leg and divide by the square root of 3. And again, to make a general case so that you kind of figure this out, all very inductive what we've just been doing, right? We've looked at some examples. So let's see if we can generalize it. So I made an equilateral triangle. Each length is 2a. And I dropped an altitude. I'm really good at that talking right anyway, so don't bother looking at it. Equilateral triangle, each side is 2a. Here is an altitude. Each side of the triangle measures 2a. So this is 60. This is 60. We've proved this before if you have an equilateral or even an isosceles, but this actually is a bisector, as well as up here. So these are 30 degrees. And so each side here is going to be a. So the side opposite the 30, I can see that is half of the hypotenuse. And then how did I get here? Just put that in here again. A squared plus the height squared is 2a squared, which is 4a squared. So height squared is subtract a squared from both sides. So the height is going to be the square root of 3a squared. Well, I can take the square root of it, that's a. But I can't take the square root of that. So my height is a square root of 3. So we can use Pythagorean theorem to kind of prove that it's going to work in the general case as well as the ones that we looked at. Oh, that's good. That's a good thing. So looking at just a couple of examples now, this is x and this is x. What do I know about these two angles then? What do they have to be? They both have to be 45. Why do they both have to be 45? Yeah, how's that? Yeah, what's that theorem? What's that base angle theorem? You have two congruent sides. If you have an isosceles triangle, then the base angles are congruent. Well, I know these two add up to 90 because this is 90. That was, I think, the corollary to the triangle sum theorem, right? Because everything adds up to 180. So if this one's 90, these have to add up to 90. So they have to be equal at 45 and 45. This is a special triangle. So I know the hypotenuse is 9 rad 2. So what is each side? 9. I heard it. Somebody said it. How do we know that? Yeah? It's a special triangle. We've already proven that if you know the hypotenuse, divide by radical 2 to get a side. And these are going to cancel out and get 9. Let's look at this guy now. See? Same measurements here, right? So these are congruent. So this must be a 45, 45, 90. So I know each leg is 15 radical 2. How do I find the hypotenuse? I feel like nobody's getting this. Maybe a couple people. How do I find it? How do I find it, Rachel? Oh, rad 2 times rad 2, 2 times 15, 30. Oh, this is a 30, 60, 90 triangle. The side opposite the 30. The shorter leg is 7 radical 3. Well, first of all, I didn't even ask for it, but what is the hypotenuse going to be? I'm going to ask for it. I'm going to make a Y here. What's the hypotenuse, Michelle? 14. Well, 14 what? Oh, 3. Right? It's this side times 2 will give you the hypotenuse. Now, how do I find the side opposite the 60 if I know the shorter side? Yeah. 7 radical 3 times radical 3. This short side times radical 3 will give you the other side. Rad 3 times rad 3. 3 times 7. So this is 21. I don't have to use my Pythagorean theorem. Special drawing. You will get really fast at this there. That's a good part. All right, let's try this guy again. 30, 60, 90 triangle. Now, what do I know? I know the side opposite the 60. The bigger leg. So how do I find the shorter leg? Yeah? Divided by rad 3. So this is 5. Oops, that's this side, I'm sorry. That's the shorter leg. So then what's the hypotenuse? Yeah? 10. You multiply the shorter side times 2. Even though they didn't ask for it, you could have said divide by radical 3 and then multiply by 2. I find it easier to do it in little pieces. The pieces that we know. How about, what's going on here? This is a 60. What is this angle going to be then? Has to be 30 because this is a right angle. I like writing them in. I can see it now. So let's see. What do I know? I know the side opposite the 60. So can I find the side opposite the 30? How do I do that? Divide by radical 3. So this is 3. And then how do I find the hypotenuse? It's the side opposite the 30, that shorter side, times 2. So there's the 33, 3 rad 3, and that is 2. Yeah. This is the side opposite the 30. It's the shorter leg. The shorter leg is the longer leg divided by radical 3. Oh, yeah. Or you could say the shorter leg times radical 3 is the longer leg. You can do it that way. And then what's going on here? 4, 4, 4. What kind of triangle is this? So that means each angle is 60, right? Well, that's, a right angle here. So what's these little pieces? They have to be 30s. Because otherwise that little triangle wouldn't add up to 180. So let's see. What is B? What do you think, Michelle? 2 radical 3. In a 30, 60, 90, you take the side opposite the 30 and you multiply by radical 3. The 45, 45, 90 is when the radical 2 comes into play. Oh my goodness. What do you think? It's going to take a little practice, right? Right. Luckily, we happen to have a little practice on this last page here. First, before we do that, questions. You want to keep that little formulas kind of nearby until they become right in your head here. So I would like you to try these as you try. Okay? So here's the special right triangles. Don't forget that. Remember how those were? The altitude is the geometric mean of the two segments, and a leg is the geometric mean of the segment closest to it, and the entire whole side of this big hypotenuse. Right? That's the theorem you're going to use for these fields. And then you're working the 45, 45, 90, 30, 60, 90 to do these other ones. So go ahead and give it a try. All right, so here's a couple ways. And the first way that I saw how to do this was I said, okay, I have a leg. My theorem says that this 5 is the geometric mean of what? Of what? 3, right? This little piece. And whole thing. sure you understand where this is coming from, because you won't be able to do your homework or this whole concept if you don't ask me right now. You see this? Now some other people did some very interesting thing. They said, oh look, this is the right triangle. If this one's 3 and this one's 5, what's this? 4. And they said, well, 4 is the geometric mean of what? The two segments. The geometric mean of 3 and the x. Either way, you're going to get the same result. Because how do you get these things out of jail here? Square both sides. So what is 5 squared? That's 25. What is this whole thing squared? Whatever is under the radical. So 25 equals 3x plus 9. 3x equals 16. And x equals 16 over 3. The nearest 10. 5.3. What about this one? How do you get this out of jail? Square both sides. Same thing. X becomes 16 over 3. So there's more than one way to do this sometimes. Question, question, question. I don't go home and be like, I have no idea. Okay, this one's a little, I don't know, I guess there's a couple of ways to approach this. Anybody get this? Yeah, how did you do this, Cody? You didn't get it. Okay, anybody? There are a couple of different ways. I kind of looked at it as saying, well, gee, to find this, it's the geometric mean of this piece and this piece, right? But I only know the whole measurement. Well, what else do I know? I know the sides. So I can do this, 20, is the geometric mean of something I don't know, and I'm going to call this one A and this one B. A times 10 rad 13, is that right? Isn't it? So then I can get A by squaring both sides. Kind of gets it right out of jail. So what's A? It's 400 over 10 radical 13. And I just used my calculator, because luckily I'm going to the nearest 10th here. What did I get? 11.1, I think? I think that's what it came out to. And so that's this piece. And then I did the same thing on that side. I said, well, let's see. 30 is the geometric mean of B, right, the side closest to it, and that whole thing. So 900, squaring both sides, gets this big square root done. To find B, I divided by this. And what are 900 divided by 10 rad 13? I put it in my calculator. 25, I think, approximately, roughly. So you need to do this too. I may have made a mistake. Is that good enough? So now I know both these sides. So can I find x? It's the geometric mean of 11.1 times 25-ish, right? And I believe I got 16.7. But again, you need to do this. You need to kind of go and see that, oh, okay, I can kind of see that. You also need to ask a question right now if you have it. Okay. Third one, I think we should be able to do. But this one, I just want to point out, the x is the entire thing, and this little piece is 5. I mean, I think that was hard to see on the picture. Anybody get past that? So just look at a couple of these. Can you do these at all? Yes? What's x for this one? 4. How'd you get 4? You take a side and you multiply by the square root of 2. The square root of 2 times the square root of 2 is 2 times 2. What about this one? Why is it just 12? How come? Yeah. So if you have a hypotenuse, just divide by the radical. Just kind of undo that. 30, 60, 90. Oh, goodness gracious. The side opposite to 30 is 2 radical 3. So what does that say about the hypotenuse? I always think that's a little easier. What is it? Hypotenuse? It's twice the length of the side opposite to 30. They're trying to trick you. I'm trying to trick you. And then how do I find the side opposite to 60? It's the shorter leg times what? Times square root 3. Square root 3 times square root 3 is 3 times 2. 60. The bigger leg is 8. How can I find the shorter leg? Divide by the square root of 3, because the shorter leg times the square root of 3 is the longer leg. Uh-oh, remember how to do this? Rationalize the denominator. So you get 8 rad 3 over 3. Anybody remember this at all? Rationalizing the denominator. We multiply by the same thing on the bottom and the top, and then I get this. So what is y? That's the side opposite 30, the shorter leg. Multiply that leg by 2 to get the hypotenuse. So just because the numbers are not convenient, it's still the same thing. I'm going to let you work on these things while I hand out homework. These are the answers to this one. So if you want to check your work, I'll put this up hopefully by tonight. You may want to review some of the video, right? You may want to review some of it if you're having some trouble with it. Mostly just memorizing some theorems.